Our speaker is Professor Marek Biesiada. His talk is about measuring the speed of light on extragalactic objects. Marku, please begin your talk.
Thank you very much. Thank you, Wodek, first of all, for the invitation, for introducing me and for the invitation. It is really my honor to present this talk in front of this audience. I wouldn't dare to undertake this having not been invited explicitly. Because my talk will not refer to high-tech theoretical issues, not even to say relativity, which is the main topic of these seminars. However, I mean, measuring the speed of light. Speed of light underlies theory of relativity. So let us begin the journey. To begin with, let us recall that the first measurements of the speed of light ever made in human history were made by astronomers. The older Roemer, who observed the moons of Jupiter, recording the eclipses of Io. You have to remember that in the 17th century, these moons have been used in the navigation across the oceans, when after a storm the pendulum clocks get unsynchronized, so the clocks on the sky in these guise of the moons of Jupiter were the perfect way to recover, to reset the synchronized clocks. And Roemer observed that depending on the position of Earth on these orbits, the predicted times of eclipses differ, and rightly interpreted this as a result of a finite speed of propagation of light that in some times when the Jupiter and Earth are all on the opposite side of the Sun, needs to cross the diameter of the Earth orbit. Next and much more precise, almost agreeing with what we know today about the value of C, were the measurements of James Bradley, who measured the aberration of light, seeking for the holy grail of astronomy at that time for the annual parallax. The humanity needed to wait almost a century for the measurement of the parallax of the closest star. However, James Bradley discovered aberration of light, interpreted it rightly, and measured the velocity of light as compared to the orbital velocity of Earth. Well, since then, talking about the history of the measurements of C could fill the whole seminar, and the whole seminar could be easily devoted to discuss all these fascinating things. However, as you all know, at present, the value of the speed of light, the most precise value, has been measured in our laboratories. With an exquisite precision, 10 to minus 9. Well, it is an issue to which I will digress in a moment, because the standards of units of time and length have changed even since my primary and high school education, and now refer to atomic processes, and the C is inherently involved in the definition of these standards, and therefore now within the SI standards, the speed of light has an integer value. Well, the story of the constancy of the velocity of light revives in the 90s, last century, where first it was John Moffat who proposed the varying speed of light theory as a cure for the cosmological problems of these days, which were the flatness problem, the horizon problem, solved by the paradigm of inflationary models. And along this, the same reasoning, João Magejo and Albrecht in 1999 proposed varying speed of light as an alternative to inflationary paradigm. And lots of prominent physicists joined them in their efforts, like John Barrow, Lee Smolin, and others. Well, intuitively, it is quite clear because inflation works. How inflation works, one can understand contemplating the light cones. I mean, the scales crossing and entering the horizon. And because the light cone in cosmology depends not only on the scale factor, but also the light cone itself is determined by C. So the idea of letting C vary with time can be at least in a naive way equivalent to how inflationary models work. Soon thereafter, there were sobering remarks by the prominent physicists like Michael Duff, who said that only dimensionless constants like the fine structure constant are legitimate subject of physical inquiry. Then John Ellis and Jean-Paul Uzan have pointed out that C does not only underlies relativity and defines the light cone, but it is also intimately connected with the Maxwell's equations, from which the C square is an inverse product of permeability and permittivity of a vacuum. And by the way, this is one of the ways that people measured the speed of light in the laboratory. So the story began, and in a modern revival of measuring or proving these varying speed of light theories have been attempted in 2015 by our colleagues from Szczecin Cosmology Group, Vincenzo Salzano, Mariusz Dąbrowski, and Ruz Laskos, who published a paper in Physical Review Letters. And their idea was the following. First, let us recall that in cosmology, I mean, the present cosmology is based on the homogeneous and isotropic Friedman-Lemaitre Robertson-Walker models. So we have a scale factor which scales the spatial distances, and there are three distances in cosmology commonly used. One is the comoving distance. The comoving distance is really the distance that stems from the metric, but it is not measurable. One cannot measure or observe the comoving distance to the object. What is observable is the redshift, and therefore in all this parametrization, instead of the physical degree of freedom, which is an A as a function of t, of cosmic time, we would rather parameterize it, that quantities, as a function of the redshift, because redshift is a measurable quantity. So comoving distance is given by an integral of c over the Hubble function, the logarithmic derivative of a scale factor expressed in as a function of redshift. It has a clear geometric and physical meaning, but is unobservable. And there are two notions of distances which are observable provided we have a special classes of objects. First is the luminosity distance, and whenever we have a standard candle, which is an object whose power of emission called luminosity can be calibrated, then from the observed flux, observed magnitude of such an object, one can infer the distance, taking into account that the flux diminishes as an inverse square of a distance, and this is called the luminosity distance. The second one is the angular diameter distance, and the underlying idea is that when we have an object of the definite size, the size that we know, and we measure the angular diameter of this object, we can calculate the distance from simple geometrical reasoning. And these three distances, fortunately, are closely related to each other by a factor of 1 plus z. And now one can see that the angular diameter distance, because of this inverse dependence of 1 plus z, unlike the luminosity distance, it rises at low redshifts, then reaches a maximum and falls down. This picture is not quite realistic. This is just for an illustration. I mean, this maximum, in fact, is not so sharp, as will be seen on the plots recovered from the real data. But just for an illustrative purpose, the diameter, the distance, angular diameter distance behaves in this way. It reaches some maximum at some redshift and then falls down. So this is the condition for having an extremum, and one can take a look at the definitions of distances and convince very simply that this condition translates to this relation, that the product of the angular diameter distance corresponding to the maximal to the redshift when the dAz function gets the maximum times the expansion rate at the redshift should be equal to the velocity of light. So one, of course, expects that this C from now on, because we have in mind possible deviations, or we have in mind the possibility, tacit possibility, that the speed of light may not be really fundamental constant, may vary across the history of the universe. So from now on, I will make a distinction in notation that, but C naught denoting the standard speed of light, the speed of light as we know it. So this calculated from such a condition, the product of the expansion rate and the angular diameter distance corresponding to the redshift of maximum should be equal to C. Well, so then the idea of Salzano, Dombrowski, and Laskos was to use for that purpose the BAO, baryonic acoustic oscillations. So let us briefly remind what they are. Baryonic acoustic oscillations are the leftovers of the quite early universe in which the baryon, ionized baryon plasma was in the equilibrium with the radiation field before the decoupling, before the last scattering, and over densities of matter produced were counter-reacted by the radiation pressure, which overthrow and induce the acoustic, the pressure waves in this plasma, which are of an acoustic wave nature. And the imprints of this process have been really recorded by analyzing the anisotropies of the temperature fluctuations in the cosmic microwave background. This is the famous pictures of the power spectrum of the fluctuations from Planck. And because these fluctuations were the seeds of large-scale structure that evolved thereafter, one expected to see the imprint in the correlation function between the galaxies, and this imprint, this small bump here, is called the baryonic acoustic oscillations recorded on the distribution of galaxies. And this from the first observation of this peak, this evolved into a very rich and fertile field of research. And in particular, I mean, getting back to the idea of Salzano, Dąbrowski, and Laskos, there has been an idea due to Charles Alcock and Bogdan Paczyński from the late 80s of 20th century, with the arguments going as follows. If we have a spherical configuration in the cosmos, the size of which is for some reasons known for us, and we can measure the angular diameter of this structure, and as well we can measure from the redshifts of the closest and the farthest part of this structure. In other words, we can measure the perpendicular and longitudinal parallel dimensions along the line of size. Then this perpendicular dimension is given by the angular dimension times d theta, the angular scale, and this perpendicular the dimension, and parallel dimension is, as we remember from this from this definition of the comoving distance, is just the increment of the comoving size. These two values should be equal, and in other words, Paczyński and Alcock concluded that whenever we have the measurement of hz times the az, it should be equal to c, and then can serve as a test of cosmological models, or this consistency can be used to tune the parameters of a cosmological model. Originally, Paczyński and Alcock have in mind galaxy clusters. Of course, they are not spherical, but of course, but the baryonic acoustic oscillations, which are the leftovers of the acoustic horizon, the sphere, the sphere of a radius of the maximum length in which the sound speed can travel until the last scatter, until the decoupling. We have indeed the spherical configurations. So whenever we get the possibility of independently measuring the transverse and longitudinal baryonic acoustic oscillations, we can use it for the purpose suggested by Salzano, Dąbrowski, and Laskos. And this is a figure borrowed from their PRL paper, showing the idea that from the perpendicular BAO effect matched with longitudinal effect, one can identify the maximum, this Z maximum, and from this relation and obtain Z maximum, one can calculate the speed of light. Leaving apart that in some fine details is a little bit circular, but the implementation has been left by them for the future when the radial and tangential BAO modes will be accurately measured. It is not possible now to use it yet. So a few years later, we, with my Chinese colleagues, we have performed the first measurement along this idea. So recall, we needed to have the angular diameter distance, obtain the redshift corresponding to X maximum, and we should have the expansion rate corresponding to the Z max. So for that purpose, we have used passing evolving galaxies as a source of measurements of Hz, the expansion rate at different redshifts. In a moment, I will briefly explain you what they are. And the angular diameter distance has been obtained from the unique sample of intermediate compact radio quasars, which we have earlier calibrated as standard rulers. So let me show you briefly what are these probes. So cosmic chronometers, the passively evolving galaxies, are the source of the of measurements of expansion rate at the given redshift. Underlying relation is this one, which dates back to the Jimenez and Leb paper. By the way, it was a paper discussing the so-called redshift drift. I will not digress upon this issue, which itself is very interesting. This equation is nothing but the writing Hz as a function of redshift. It is a definition from in terms of the scale factor, but in terms of redshift is this equation. So whenever we have a bunch of objects for which differ not very much in redshifts, it is a dz, infinitesimal difference. So in practice, small increment in z, and whenever we are able to identify the cosmic time difference, meaning the age difference between these two galaxies, we can provide the measurement of the expansion rate at the given redshift. And which redshift? In practice, it is a median, the redshift related to the median of this z, and the median of this increment dz in which we measure two objects. So the difference in the age of galaxies can fortunately be measured, not in every galaxies, in the so-called passive evolving galaxies. In fact, there are elliptical galaxies in which there is no more star formation, and they passively evolve, meaning that nothing new is happening. No new stars are being produced in these galaxies, but they just evolve according to the already possessed population getting older and older. And how to determine the age difference? Fortunately, one is able to relate the age difference between the galaxies based on the spectral feature called D4000, which is the break on at the 4000 angstrom. This break, which is an analogous to much better known Lyman break in the spectra of stars, is a result of the onset of series of metal absorption features. It is known to correlate with the age of of the galaxy. So this is the idea how it is defined as a ratio of fluxes, continuum fluxes in the red and blue bands, and this is the definition of what is a red band and a blue band in the spectrum. And this relation between the D4000 and the H has been calibrated on different stellar population synthesis models of galaxies. And according to this technique, Michele Moresco has identified a sample of 31 well-measured HZ values spanning the redshifts from 0.1 up to redshift of 2. So HZ, we do have the sample of objects that can give us this information. What about the angular diameter distance, the standard ruler? And the standard ruler that we elaborated with Chinese colleagues was based on the compact radio sources, and the radio sources, quasars, AGNs are all the same. I mean, there is a unified picture of the active galactic nuclei, giving rise to the objects that we call the quasars, blazars, radio sources like FR1, Fanarov relay type 1, type 2, and so on. And the unified picture is that we have a central black hole in the galaxy surrounded by an accretion disk. Then at the outskirts, the dusty torus is formed, and along the rotation axis, the jets of emissions giving rise to radio emission are emitted, and this disk structure is surrounded by the hot corona. So compact radio sources that are our prime objects are the configuration in which we are looking along the jet. So the angular size of such an object is the size of the base of the jet. But what is the base of the jet? Just like what is the photosphere of the sun. The sun is dispersed up to interplanetary space. Okay, that does not have a rigid solid boundary, but the well-defined quantity is the surface of a unit optical depth, and in the sun it reproduces this well-defined photosphere, and the same is here. The base of the jet is this portion of a jet in which the optical depth is unit, and optical depth is related to opacity mechanism, and the opacity mechanism in this case is the self-synchrotron self-absorption. And it has been proposed since the late 70s that this model has been proposed, and Blandford and Koenig derived the relation how the size of the base of a jet should evolve with the radio frequency that we observe, 1 over frequency, right? And then we have took the old study of Preston comprising 1,398 radio sources, including 917 compact. We analyzed, split it into the subsamples and analyzed their linear sizes, angular sizes from the data, and we looked how they relate to the physical metric sizes of the core. And in order to allow for evolutionary effects, we parameterize this as a function of the luminosity of the radio source and as a function of redshift, because in the radio domain, many radio sources display, and it has been known for long, display a noticeable evolution with redshift. And we concluded that only radio quasars are promising, in the sense that these exponents in the power law relations are close to zero. So we identified the subsample of compact radio sources and calibrated them further. First of all, with the expansion rate reconstructed from HZ, which we didn't need to assume any cosmological models, just from the data, cosmic chronometers. It served for the purpose of a robust selection of the luminosity sample, because for the luminosity we observe the flux. So for the calculating luminosity, we need the distance. Then we calibrated the standard rulers, which have the less dependence on the luminosity and redshift. Calibrated, we have identified this intermediate luminosity quasars defined in this way, and calibrated their linear sizes. And then have the angular diameter distance can be reconstructed with this calibrated size and used for various purposes. For example, we use it in one of the papers, we use it to test various cosmological models. This is an example of this. We have also verified this method at different frequencies, whether it follows the Blandford-Koenig model. So we checked the underlying assumptions, and getting back to the main subject, we have used it to measure or to obtain the speed of light along the Salzano-Dombrowski-Laskos idea. So from Gaussian processes, we reconstructed dA. You should not be, confused by this wiggly nature of this GP reconstructed, because, Gaussian processes is a reconstruction, engineering type reconstruction, which in which the behavior of the nearby sources takes a leverage, which is manifested by this. You should not take it as a physically meaningful representation of a dA in the real universe. However, it allows us to calculate the Zmax at this value, and we use the GP reconstructed HZ from cosmic chronometers, obtain the value of C within the uncertainty coinciding with the speed of light as we know it. So this was the first check of the value of C on extragalactic objects. And then we developed our new approaches to get the speed of light, based this time on strong lensing systems. So what the strong lensing is, I will not spend much time of it. It is a consequence of the bending of light by massive objects. It can be understood either in the light ray formalism or waveform formalism, that the waveforms get bent traversing through the curvature induced by massive object, and the multiple images are produced. I mean, the lesson to be taken from this picture is that what are the observables in strong lensing systems are the image positions and the shape of distortions, the time delay between the images, and the magnification ratios between the images. And these two are the most valuable ones. So the version 1 of our method was based on the following setting. If we have a strong lensing system for which we can determine the time delay between the images, and this time delay between images depends on the certain combination of distances in the optical system. It is this combination, angular diameter distance to the lens times to the source and divided by the angular diameter distance between the lens and the source. This is a recollection how the angular diameter distance relates to the comoving distance. Comoving distances between two objects at different redshifts follow the so-called distance sum rule. This is the general expression in the generally curved Friedman-Robertson-Walker model. But let us limit our attention to the flat universe, which is very well supported by CMB data. In flat universes, the comoving distances just simply add together. With a very little algebra, one can derive the value of C in terms of the distances in the system, the time delays, and the Fermat potential difference. So Fermat potential is this guy, the geometrical term, which means that that the deflected light ray travels a different distance with respect to the unlensed case, right? And this is the Newtonian potential of the lens projected to the lens planes. And these two together are called the Fermat potential. So we propose that this version of the method could be applicable in the case of the lensed supernova 1A. We are now living in the era, or waiting for the LSST on Vera Rubin Observatory LSST survey to begin, and LSST is expected to provide us hundreds of lensed supernova 1A examples. By the way, we have already recorded several lensed supernova 1A, but just only a few of them, two or three. But in the era of LSST, there will be hundreds. And therefore, the time delay between images will be very accurately determined. And any case of a strongly lensed transient event, either like a supernova 1A or a gamma ray burst or a gravitational wave coalescence, will give us a very precise measurement of the time delay, which is not attainable so accurately for the lensed quasar systems. then because it is a transient, the host galaxy will be visible, and from the lensed images of the host galaxy, and not only images positions, but also the shape distortions will allow us to accurately determine the Fermat potential. So this is the budget of the uncertainties in our method. And then the redshifts to the lens to the source, the clue is how to get the distances corresponding to the redshifts to the lens and the source. But there will be thousands of even unlensed supernova 1A discovered by LSST. And from this very rich statistics, we can have match the unlensed, different unlensed events matched by a redshift and obtain these distances. So our result was that in the era of LSST, one would be able to have 10 to minus 3 1,000th precision in the measurement of potential deviation of C from what we know today. But there is another version of using strong lensing systems, and this version, the method is essentially the same. But instead of using the time delays, one is using the image positions from which the Einstein radius can be recovered. And instead of measuring the Fermat potential, one can use the ansatz of the symmetric power law mass density profile, which so far worked well in the case of elliptical galaxies being the strong lenses. So then if one has measurements of the stellar velocity dispersions in the lensing galaxy, we can use two ingredients: mass of the lens from determined from strong lensing principles, my mass projected mass inside the Einstein radius by the measurements of image positions, and the so-called dynamical mass, which from the velocity dispersion and using the Jeans equation can be scaled to the Einstein radius by this way. The scaling originates by the power law relation of the mass density profile. So this is just one of the simplest examples. I mean, in reality, we have several versions of it in which this power law density applies with the different exponents to the luminous part of the galaxy and to the dark part. But I don't want to go deeper into these details. But the point is that combining this or demanding that these two estimates should be the same, one is able to get this expression for the Einstein radius. This usually has been used by us to constrain cosmological models, but one can solve it for C and try to use it to test the value of C suggested by such strong lensing configurations. And again, for that purpose, besides the measured values, Einstein radius, angular Einstein radius, and velocity dispersion inside the aperture of the spectrograph, and besides the redshifts, which will be measured, one needs to have angular diameter distances to the lens and to the source. At best, derived without invoking a cosmological model. And in another paper, we proposed, not as a proof of, not just as an idea, but we have proposed and tested it on the real data. And our first idea was to calculate the distances in the system by redshift matched ultra compact radio sources. I mean, this sample that I already mentioned that we use in this different methodology. And this is the plot of these 118 strong lensing systems, the scatter that it produces around the value of C, and the summary of weighted mean summary of these results, which is of course in agreement with the speed of light measured in the laboratory. Besides the standard rulers, and of course the most of the community is using the standard candles, the supernova 1A, and at the moment of publishing this paper, the Pantheon sample was the best one. It has now evolved into a Pantheon Plus sample, which is richer and a little bit better. So in this case, we have reconstructed the distances to the lens and to the source from reconstructing the luminosity distance in the Pantheon sample, and we calculated the this ZS is the ratio of the strong lensing suggested value of C to the laboratory value of C. So this should be 1, right? The advantage of this method is that we have this ratio of distances, which means that it translates into the difference of corrected apparent magnitudes in B band at different redshifts, in which this nuisance parameter, the absolute magnitude, cancels out. So this is also a technical benefit of that. So performing this test on our strong lensing systems, we obtained a fairly good agreement between the observations and the theoretical paradigm that C is always and everywhere the same as we measure in the laboratory. And the last idea that I'd like to share with you is the one that invoked the interest and is the reason of my inviting here to talk about this. Our latest paper accepted in APJ, and the idea is a bit different. If we take an expression for luminosity distance and take a derivative of the luminosity distance, we can express the velocity of light in terms of this derivative. Derivative, luminosity distance, and the hz. We would like to be a cosmological model independent, and therefore we will use the DLZ reconstructed, this time by the series, third order power series expansion in the log 1 plus z variable. So the coefficients of this expansion can be calibrated on the standard candles, or should be calibrated on standard candles, and Hz should be taken from some probes. So in this paper, we have contemplated a few ideas for the probes to be used. Either this reconstruction can be done on the supernova 1A, on the Pantheon sample, or in the quasars used as a standard candles, but in a different way. I will explain you in a moment what is our underlying idea of using the UVX correlation in quasars to calibrate them as standard candles. So in role of standard candles, two different probes can be used, and in order to obtain the expansion rate as a function of redshift, this could be, first of all, of course, done with cosmic chronometers, but also we contemplated, I mean, the future gravitational waves detections by the DCICO. So in a moment, a few words about these probes. So quasars as standard candles, it is a story that began with the Guido Risaliti and Elisabeth Lusso papers. There are earlier papers, but well-known, the best-known one is from 2019 in Nature Astronomy. They have provided a very good sample of such objects. And the idea is the following. From this, as I already show you this unified picture of the AGN, quasars are the AGNs. The correlation between the luminosity in X-rays and ultraviolet should be expected. Why? Because the ultraviolet emission originates in the accretion disk around the central black hole. And these UV photons then go through the hot corona and undergo the so-called inverse Compton scattering. This is astronomical, astrophysical jargon. I mean, this is exactly the Compton scattering, but the energetics is inversed in relation of normal Compton scattering. So lower energy photons acquire energy and became X-rays by being scattered on the very hot electrons in this corona. So this correlation should be expected, but we are not able to observe the luminosities. We are able to observe fluxes. So the transition from luminosities to fluxes involves luminosity distance, and this is exactly the idea. If we are able to calibrate this relation, the slope can be calibrated and was calibrated by fluxes in redshift beams, because if you have the redshift beams, then the relation between fluxes will be the same as the relation between luminosities, right? Because the narrow redshift beam means that they have almost the same distance. So the gamma can be calibrated from fluxes, from the redshift fluxes in redshift beams, and the intercept should be calibrated by other probes. Anyway, this is or we have the Risaliti and Lusso sample to be used as a source of luminosity distances. So this is the first of these alternative probes that I haven't explained yet. And concerning the DCIGO and gravitational waves used to provide the expansion rate, the story is following. Now we are in the era of interferometers on Earth registering gravitational waves. However, the sensitivity relates to the high frequency gravitational waves. It is an unbeatable limit of 1 Hertz, which cannot be surpassed due to what we call the seismic noise. But in fact, it is even a minute tremor of the ground induced even by the ocean waves or the vehicles or whatsoever. So 1 Hertz is an unbeatable wall here. Then we have the LISA and on the horizon with the success of LISA Pathfinder, the spacecraft triangular configuration of interferometers will be probing much lower frequencies, and lower frequencies meaning it will be sensitive to the final stages or coalescences of extremely massive black holes, those in the centers of galaxies. And there is a place in the middle, and the Japanese proposed to launch the DISIGO with the sensitivity band spanning from the millihertz to 100 hertz, so partially overlapping with ground base. And what is even more interesting, the DISIGO, its sensitivity curve will allow to detect the coalescing binary black holes or binary neutron stars days to years prior to the coalescence, prior to their entering the ground-based detectors. So, for example, the two. Oh, sorry. I mean, this should be GW17 0817, of course. Sorry for this misprint. So these two famous double binary neutron star merger and the first ever detection in 2015, they should have been detected by DISIGO and visible correspondingly for 10 days before the coalescence, or in the case of binary neutron star merger up to 7 years before. And this means that the number of cycles registered will vary to the hundreds of thousands or hundreds of millions cycles. This gives a unique opportunity to study the phase evolution of the template and the mismatch of between phases between the template and the observed signal, for example, caused by the acceleration during this time, for example, 7 years, has been proposed as a way to directly measure the acceleration of the universe. And indeed, it's been published in Physical Review Letters in 2001 by the Japanese proponents of DISIGO. By the way, this idea is very similar to the idea of the redshift drift. So from the measured phase of the signal, the so-called acceleration parameter can be measured, which relates simply with the expansion rate. So this is another way to measure the expansion rate. So our newest results for the prospects of using this method are the following. First of all, these are not prospects, but the real data made on the Pantheon sample and Relativity quasar UVX standard candles combined with cosmic chronometers give us, of course, the agreement and rather precise agreement with the value of C that we know. And these are the prospects if we imagine to use the Pantheon and quasar sample combined with the DCIGO acceleration measurement. Going to the end of my talk, let me finish by conclusions that this uncharted territory of measuring speed of light using extragalactic sources is being conquered now. Even more important from the perspective of possible varying fundamental constants are the investigations of a fine constant, structure constant, partially because it is non-dimensional, and recall my opening remarks. And there is a very good, effective, and smart methods of many multiplets developed and being used by John Webb, Victor Flambaum, and the others. And the idea is that in the spectra of quasars, you have the alkali atoms multiplets, and the multiplets, I mean, the lines are redshifted in a different way, but they are redshifted in a bulk, but the splitting in the multiplet is governed by the Rydberg constant, which means by the fine structure constant. So if in the spectrum of a quasar you have the Lyman forest absorption lines from the many clouds spanning a range of redshifts on the way between us and the quasars, and we can analyze these multiplets and look if there are any suggestions for fine structure being different than from what we know now at Earth measure. All these things, in my opinion, are just another empirical support that the laws of physics are the same on Earth now as they were in the distant universe and across its history. So, by the way, I mean, this is the famous words of Dirac. He expressed it as just a paradigm that people are tacitly assuming, but we are now in a position of empirically verify such paradigms. What will the future bring? Perhaps it will bring us the unexpected, some crack in the picture, maybe. But as for now, it could also be used as a cross-check of cosmological probes. So if in my data I will see the significant, statistically significant deviation between the sea from extragalactic objects and from the laboratory, the first thing that I will took seriously would be to check the systematics and the extragalactic data that I have. Thank you very much for your attention.
Well, thank you very much, Marek, for a nice talk. And now we have some time for short questions. Okay. Yes.
Marek, slide number 24, if you don't mind, because maybe
yes.
I'm telling. So is 1 in table 2 is eta equals to 1 consistent with your
Yes.
result? It is. I mean, downstairs, table 2, it's 1002 plus minus 001, okay? So eta is C to C0, okay? So...
No, So yeah, so your point is about this,
My
this-
point is this consistent with C equals to C0 then?
Okay, I mean, in case of a table 2, one should not take everything too much seriously because it is a partially based on the simulated data. So the simulated data regarding this XZ from the DeSigo. So I mean, the most informative or the lesson to be taken is the level of accuracy attainable or expected by using this value. But as for now, I mean, it is just from simulations and
Okay, it's a simulated data.
Yes.
I see. Okay. And how about your conclusion from John Webb and Victor Flambaum? Because I think, is it consistent with no varying alpha? Your conclusion, the last one, because you have not even given the paper.
Yes.
I mean, you have not given the reference.
Yes, exactly.
Exact reference.
You are right. This is the value from some of their old papers. My point here was not to discuss the state of the art, but just to suggest that there is much richer, I mean, territory to be explored. Not only varying speed of light, but also also a varying gravity constant. And of course, I have provided the bounds on the changing of G from pulsating white dwarfs once. But I just quoted the fine structure constant because of this long-standing.
I understand. But here delta alpha to alpha, is it says that it's. I mean, if I am wrong. Is it consistent with no varying?
It's consistent with no variation.
It is. Yes. Okay, it is consistent with no variation. Because of course, all of them can vary. Okay, E can vary, which is Bekenstein varying charge, in fact, model. C, as you have shown, can vary, but also some people have also considered a possibility that even H bar can vary. So all of them can vary, but my more comment is that to your first claim that Duff, of course, didn't like these dimensionful constants to actually to vary. Of course, they do not. It's obvious. What you're studying and we are talking about is the ratio C to C0. So
yes,
we in fact are working on the dimensionless numbers. So even if you take 1 meter, 1 meter means that it is 1 because you have a pattern of a meter and you take the ratio, so it's dimensionless. Okay, so it's meter
exactly.
Divided by meter, so it's 1, but we say it's meter but it's not.
Yes, exactly, and that's why starting from some papers we put it very clearly that what we are exactly, I mean, in each and every case, in your case and in our first case, it has always been the ratio that C over C0, because otherwise you should have a theory underlying, I mean, the theory of this reproducing the angular diameter distance in the cosmology stemming from the varying C method theory and so on. So when we are using the standard expressions for cosmological distances, we are tacitly assuming that what we are testing is a ratio of C over C naught, right?
Yes.
So yes, you are perfectly right that yes, and thank you for this comment, because I mean, preparing to this talk, I thought to myself that I will make this statement. At the end, I forgot, and you have did it.
We have spent
yes.
lots of hours discussing this with John Barrow, John Webb, João Maguejo, and others, including our whole group here. So we really know about it. Thank you.
Yeah.
Okay.
Our time is almost over. So one very short comment or remark, very short one.
It's Mikołaj Korzyński here. Thank you very much for a very nice talk. My short comment is that these are very interesting methods and very, very nice ideas. However, they often rely on the measurements of redshifts. In case of methods using the phase of gravitational waves, that means that they're quite the results will very much depend on any kind of peculiar motions of the objects you're looking at, no matter whether this is the strong lensing method or any other method. And this is even more so in case of measurements based on phase of gravitational waves, where I think any kind of peculiar accelerations will also contribute. So I wonder how you would comment on that.
Yes, you are absolutely right. You are absolutely right. To some extent, and to the extent that we used our samples, the standard argument of the redshift ranges making the peculiar velocities negligible can hold. However, of course, you are absolutely right that I mean it should even be examined system by system to make sure about the contamination. I mean, in some in some error budget considerations, we have ad hoc proposed such I mean components influencing the uncertainty. But yes, I agree, and you are perfectly right that peculiar motion can be relevant here. And there is one ongoing study we have with Chinese colleagues according to this technique of acceleration parameter, in which we are trying to account for the peculiar motion and even our peculiar motion with respect to the CMB. Yeah, so you are absolutely right.
Thank you very much.
Okay, so I'm afraid we have to finish. So let us thank the speaker again. And I thank everyone for participation in this seminar, and we close the meeting. Goodbye.